So I'm Charles, working for Flower Labs, the company behind the federated framework Flower. Before we start about distributed AI, are you somewhat familiar with federated learning already, or not? No? Have you ever heard of it? All right, perfect. So this is an introduction to federated learning. So this is good. We're going to start off going through the motivations behind federated learning, then an explanation of what it is, an introduction to Flower, the federated framework I'm working on, and then a few hands-on demos, and some next steps if we have time, and also some deeper topics. So first of all, why use federated learning? So along the day, we've seen different presentations talking about AI and LLMs. So going back to what's the secret recipe for AI breakthroughs, we can kind of sum it up with three essential components. First of all, the models. As you can see here, we go from very small models like AlexNet to massive models like Llama 3. Then compute, from the olden GTX days to now the Blackwell generation of NVIDIA GPUs. And then lastly, and most importantly, the data. And so this is what we'll focus on. If we look here at a few different AI milestones, we can see that, for instance, Llama 3 was trained or was pre-trained on 15 trillion tokens, Whisper on more than or about 700,000 hours of speech. So that's roughly 77 years. And OpenAI 5 was trained on 45,000 years of Dota play against itself. So those are massive amounts of data. And quoting from the Google DeepMind team developing Gemini, they say that the data quality is critical, and this is one of the most important aspects of their research, finding good data and training models with it. This is from the Meta team, arriving to roughly the same conclusion. And they also arrive at the conclusion that we seem to be arriving at some kind of upper limit of publicly available data. Even if we ask Gemini itself, it will tell you that this issue with data quality is worsening over time, and that according to an AI research institute, all high-quality data will be exhausted by 2026. I'm not sure if this is just hallucinating, but it's an interesting perspective. And we have to keep in mind that this is only talking about publicly available data. And if we look here, so this is actually close to what we saw with the Llama 3 model, 15 trillion tokens for the web data that's publicly available. But now, if we look at the private data, we can see that, for instance, all stored instant messages are 650 trillion tokens, and all stored emails more than So to put that in perspective, this is what those numbers look like on a graph. And so we have this huge amount of data that we can't harness. And one challenge also is that it's naturally decentralized. So it's going to be on a private computer somewhere, or a data center, or even a smartphone. And AI cannot use most of it. And collecting data, apart from being a privacy concern, because obviously you don't want to share your private emails to big corporations, it's also impractical to just collect everything in terms of infrastructure or even end user devices. And so one solution to solve this, you probably guessed it by now, but it is to, instead of collecting everything in a central server and training a model on it, actually going to the end devices and train models on device. So if we kind of look at what's happening, so this is the most common way of doing things, where you have different devices collecting data at different levels, and they're all sending their data to a server to then train a model on it. And what we propose to do is to, instead of moving the data to the server, moving the actual computation to the devices that hold the data. So here, in this case, the data stays where it originates, and there's no need to share private information. And another aspect that's important to consider is that if we're talking about distributed infrastructures, there is another way we can scale. Instead of just buying more and more GPUs, we can leverage those huge federations of devices and actually train smaller parts of the compute smaller parts of the training on many different devices, and that could allow us to have even more compute than today. And so all of this leads us to federated learning. So the goal of federated learning is to be able to leverage all of this data without actually having to share it, as we said. So the first step with federated learning is that we have an AI model we want to federate. So that would be some kind of model that's initialized with random weights, for instance. It's just defining the architecture we want to train. And then we're going to send this model to different devices. So here in this case, those devices are smartphones, but it's just for illustration's sake. That could be computers, data centers, whole organizations. And so once they receive this model, we assume that they each hold some data that could be used for training this model, and so they perform this local training step. And so this is also important, is that obviously all devices do not have the same computing capacity, so each will do what they can. So if you have a very powerful computer, you'll be able to maybe train more. And so once this training is done, you send back the updated weights to the server. So in this case, you have no data sharing. It's just the resulting computations you did to train the model. And so finally, on the server, you will receive, so in this case, all 3 weights, and you do an aggregation. So this is, you have different strategies to do this. We'll go in maybe a bit over this later. But in this case, you could do a simple average of all the weights to have a new model. And then what you do is that you just repeat those steps until you get good enough results, or you converge. And so this is essentially what federated learning is. And this is just saying that one loop of this, we usually call this a round of training. So you have a nice visual here that illustrate this, where the model is sent to the devices. It's training on the data that they hold, and then going back to the server, and then you do many back and forth. And so just to touch upon what happens on the server side, the aggregation, as I mentioned, this is one of the most standard way of doing it. This is the paper that introduced this, as well as the concept of federated learning. And the most common way is to just use this function, which is just a weighted average. So essentially, you take all the weights you have, and you weigh them by the number of data samples they were trained on, and then you average them. So this is, for instance, if you have a client that only trained on 2 data points, it shouldn't be weighed the same as a client that trained on thousands and thousands of data points. And then you have different subsets of federated AI or federated analytics. For instance, you can also evaluate in a federated way, where you send a model and then you just evaluate the model performance on each device. You can also have simple analytics. For instance, you have a distributed data set on many clients, and you want to do some kind of to compute some metric on them. You can do that. But then one thing you have to keep in mind is that the idea behind federated learning is to be somewhat private, but privacy comes with cost, which is complexity, I would say, because you have many different places where you could have security breaches. And so this is important to keep in mind. You cannot just have federated learning system and say, okay, it's good, it's secure, it's private. Then this is not how it works, unfortunately. You have to be wary of many details because you have so many interactions and communication steps. So for instance, from the client to the server, you should minimize the data exposure. You should also anonymize the what you collect from the different clients. There are always ways that we could theoretically reverse engineer some of the weights to access some data. So it's important to, for instance, add noise. And there are many different methods that you can use to make sure that your system is private and secure. And this leads us naturally to Flower, which aims to solve most of those issues. Sorry, here's the nice flower animation. And so the framework aims to be as simple as possible to use, but also very extensible, providing many different features out of the box. And so the goal is to make those deployments, especially in production, where you need those high privacy and security requirements, to make those baked in the framework and easy to use. And so one of the good things as well is that the framework is fully open source, so it can be used freely, cloned, forked as other projects, and you can also contribute to the framework if you're interested in that. And one thing that's very important to us is that it's easy to go from development, so in single machine you just play around with something, to actual deployment. So all of this should be very easy for the developer to go through. There shouldn't be any hurdles to go from one step to the other. And we'll go over this in the actual demo afterwards. So here, this is just highlighting some of the research made for Flower and the rough architecture of the client and the server. I don't think we need to go over this. And then going back to the diagram I had before, we aim to provide those guarantees out of the box. This is going over the simulation performance. So we want the framework to be as fast as possible, so you can iterate quickly on the work you're doing. And we also want to be compatible with most of the frameworks that developers use. So if you are already training ML or AI models in a centralized way, you can just quickly, as a drop-in replacement, use Flower for those. And we'll go over how later on. All right, so just a quick aside, we also developed a datasets library because I mentioned simulations before. So in a federated setting, obviously the data is not centralized. It's distributed among clients, and you want to be able to simulate this. And so we created this dataset library to be able to partition the data simply. So for instance, you could simulate a situation where you have 10 clients and each of them hold data with a particular data distribution. And I'm sorry, I'm going over this pretty quickly because if you have questions, feel free to ask them. We can always go over this later. But I think the demos are going to be the most interesting for you. And so yeah, this is just showing how easy you can set up a partitioner for a data set. And we also have a set of Flower, what we call Flower baselines, where those are different papers that we implement in Flower. So this is important for us to be close to the research and to allow research groups and researchers to be able to assess the performance of their new methods against previous methods. And we thought this was a bit lacking in the current literature, where the results were not necessarily easily reproducible. So we wanted to change this with this initiative. And finally, we have quite a big community. And this is very important for us because being an open source framework, we rely heavily on open source contributions. And also we have a Slack channel I think I skipped over this at the beginning, but that you can join to ask us questions or feature requests. And here's an overview of the contributors. And we also have a forum, Discuss forum, so you can get answers pretty quickly there. And so I'm going to go over the demo now. So first thing I wanted to mention is that you can go over the docs in case you have specific questions about how Flower works or how to implement certain things. But now, so if you have your machine, this is the time to actually do something with it. A first demo I wanted to show is just creating a Flower app and installing it. So this is this is not the most important part that you have to run on your machine. So if you want to do it, all right. So let me just. I'll actually go. Okay, I'll create a new project. So here I already have Flower installed. But if you have not, you can just install it with this command. I'm actually going to also install the simulations extension. And so, yeah, so it's already installed for me. And then once you have this installed, you can just run. So I'll just run Flower new, and this will prompt me for an app name. So I'll just call it GDG. Then my username, this can be whatever. It's just for specifying the author of the app inside the PyProject.toml. And here in this case, I'll just choose NumPy because it's the most simple app. And then now, if I go inside the folder, I will install the current project. So we'll install the dependencies, and now it essentially created, I guess 3 things, but mainly the PyProject.toml, which defines all the configuration, and then it also created a folder, GDG, where we have what we call the client app and the server app. And so those are going to define the So the server app is going to define what happens on the server side, so which aggregation strategy we choose, for instance. And then the client app defines what the client actually does. So in this case, it's very simple because we just want to show the structure of the code. So in this case, the fit function, which is touch that. The fit function, which is supposed to be the function to train locally. Here, in this case, it just gets dummy model. If we go into this function, it just returns a small array of ones. And so this is what we return, and then the evaluate function, which is supposed to be the function used to federated evaluation, is just going to return 0 as the loss and 1 as the accuracy. And so here we have all of that. So if you've if you did the flower new command, you should have something very similar to this. And just a quick note, in the PyProject.toml, we have here a section for the app config. So in this case, by default, it's going to do 3 server rounds. So here, if I go there and now do flow run, it will run for 3 rounds. So in this case, without specifying anything, it's going to run on in simulation mode. So this is just spawning the clients in memory and simulating those clients. So it's not actual clients on the network. All right, so that was just for simulations. So this is what we went through with simulation in this case. And now I want to quickly touch upon what we call federations. So this is a concept where you have different, we call them supernodes, but those represent different devices. And so those supernodes are going to be able to connect to a superlink. And those will, each of those components will be passive, so they'll just do nothing waiting for calls, so they won't require any resources. And then what we can do as a developer or a data scientist, we can then write those server and client apps that we've just seen and then send them to the superlink, and the superlink will send it to the available devices. And so we can do that concurrently with multiple people. And so each time it will distribute to the connected supernodes. And so what I wanted to propose is that we actually create a small federation. So I set up, you can go to flower.run, so flwr.run. And there you should see instructions. Instructions to join the federation. If I'm able to, I will show you just. All right. So you have 2 options, either with Docker. So if you have already Docker installed, or Docker running on your PC. Otherwise, you can just install Flower and then copy this command. So you can just copy here. And so I think, yeah, I already have it running on my machine. And very importantly, sorry, I forgot about that. Very importantly, you need to download the SSL certificate. So this application is secure. So we have SSL encryption for the traffic. And then once you'll choose a download location, and you have to specify the location here if you use Docker. And here, I would advise actually using an absolute path, not with the home replacement here, for the root certificate. And so, okay, and so then I will actually I'll just go over there. Okay, let me. Whoop. Okay. So let me know if you're able to set up the certificate. I've already set up some different machines that are connected to the sublink in case you're not able to connect to it. And so here, so this is the Superlink logs. So this is just what we see where every, I think, yeah, every 3 seconds it's gonna ping the different so elements of the architecture to check if there are any messages to treat. All right, so I'll just show you if I'm just gonna with this. So okay, and so now once we have this federation running, we can actually go inside the PyProject.toml. So that would apply to the project you just created. And there you can add, so I'm not sure if it's big enough, but you can add a new, what we call a federation. So by specifying the address of the federation, as well as the path for the root certificates. So that's to be able to connect to the SSL encrypted channel. And so once we have this set up, instead of running what we had before, which was just flower run, we will add this dot to specify the which project we want to run, so the current folder. And then GDG, just this is the federation name. And so in this case, if I just run this, it will create the run. And then it won't print anything, but it will create the run. So this means that the code is actually sent to the different supernodes. So I'm not sure if anyone was able to connect, but if you were connected, you would receive the code. It would run, and then here I can either, I think it's, I can either follow like this, or I will actually just, it's simpler for me. I will start another run and add this stream flag, which allows me to follow what happens on the server side. And so note that those two runs are different. So I could have changed some values in the code and it would be deployed on the machines differently. And so yeah, here we have 4 clients. So we can see, yeah, I think the strategy by default is just sampling like 50% of the clients, and for the evaluation, it's actually taking all of the clients. All right, and so as we saw by default, it's just 3 rounds. And if we okay, and so now I just wanted to show if I modify, for instance, the number of rounds, I will just put 2 rounds. Whoops. And then here in the client app, I can say, so here, for instance, I can just add and here, so yes, so I'll start a new run, and now it will ship this new version of the code to the different clients. And so now all of the clients that were connected will actually on their terminal, they will print this hello from GDG Mons. And so, and it will only run for 2 rounds. this will be done. Yeah. All right, so going back to, so yes, we already went through that. And now just a few examples. This is an example. We actually have this on the GitHub repo. So the GitHub repo is just github.com/adapt/flower. And so we were able to fine-tune OpenAI's Whisper. So it's a model for speech to text with Raspberry Pis using Flower. And we actually got pretty good results. And we also fine-tune a vision transformer on a single GPU. So this is done with our simulation engine, because the simulation engine will allocate the resources accordingly. So if you have a single GPU, it will either split it to the different clients or run sequentially depending on the resources you have available. And also fine-tuning of an LLM. So in terms of next steps, I wanted to highlight a few things. So feel free to go to the website to learn more about Flower. We have the documentation there, some blog posts, and also you can join the Slack channel. So this is useful if you want to talk to us, but also share some contributions or just introduce yourself and meet other like-minded students or researchers. And then we also have this event that we host. This will take place in March of next year. So it will be in London and also online. So you can just register here, even if it's online. And we'll make some big announcements, as well as some many different demos and activities for people there. And we'll also try to organize exciting stuff for the online people. And then we also have this competition right now, which we call the LLM leaderboard. And this is, so the goal is to provide 4 different challenges and to allow people to compete on improving LLM trained on federated data or distributed data. We also have a deeplearning.ai course. So if you want some other resources that are video-based, that can be very useful. And yeah, the GitHub repo, which is the most important place for us. You can also open pull requests and issues there. All right, and so that's about it. I mean, I have other slides going more in depth, especially into different aggregation strategies, but I'm not sure if you want to go there. Feel free to ask me any questions. I can go through them if you want, but